Today we're just going to give you an introduction into what are the bonded systems that we've been introducing here into the UK and all over the world. We'll do it in two parts because I think just one person giving slides by death show can be slideshow by death can be quite boring. So we'll hand over to George in a minute to go through just a brief sort of company history, some milestones that we've gone through. George will roughly introduce the main products that we're introducing here in the UK, and then I'll come in and talk about some of the more technical side of the presentation. And then towards the end, because George has been with the company 20 odd years, so we've got some references there to show. And George will talk about those as well, and then obviously questions at the end. So I guess we just have to acknowledge a couple of people. So again, thanks Mike for organising us to eventually come here and speak. We've been trying to do this for a little while now. The Delcor fasteners have been installed here in London almost 10 years, if not 10 years now. So this is quite fitting now, I guess, that we come and actually explain what it is that you're putting in. We do also have to acknowledge our local partners here, Tyflex. You know, whenever you introduce a new technology to a very well-established railway like you have here in London, it takes a lot of work, and these guys have sort of stood by us through that. It can roughly take about 10 years really before technology is truly accepted and becomes standard. So those guys, Tom, Matt, and especially Peter, we do have to acknowledge and thanks those guys for that work. All right, I'll hand over to George just to go through a brief company profile, and then I'll come back in and get into some more technical stuff.
Thanks, Luke.
Thanks again.
Thanks, Luke. Welcome, everyone. As Luke said, George Stamboulis, the Marketing Director for Delcor Rail. So I've been with Delcor 27 years. I just want to go through a bit of a history of Delcor. So Delcor was established back in 1983 in Australia. Initially working in the mining sector, designing, manufacturing, dewatering, conveyor belt systems and dewatering systems for the mining sector. And part of their range was a rubber belt, which they were importing from Germany, from a company called Kluth Gummy Works or Kluth Rubber Works. And Kluth were based in Cologne in Germany, who had been working with the Cologne Transit Authority, who designed the original Cologne egg baseplate. Okay, so the history of the base plate with Delcor goes back to 1983. At that time, Delcor got a license to basically distribute that base plate in Australia only and parts of Southeast Asia. And in 1987, 4 years after they introduced the product, we installed it on the Sydney Metro underground in a very sensitive area where the music of the Conservatorium of Music was being extended and coming closer to the rail tunnel. So there was a concern about noise and vibration, and we somehow heard about, I was actually working for the railways back then, so I was on the design team for this particular project. We heard about this Cologne egg plate and we decided to give it a trial. It was installed in 1987, it's still there today, and it worked very, very well. As we moved forward, in 1997, I joined the company in 96. In 1997, we were able to win our first export project in Hong Kong on the Lantau Airport rail link, the new airport they were building in Hong Kong. And at that time, it was a really big thing for Delcor to be manufacturing in Australia and exporting overseas to Hong Kong. Those base plates were installed on all the platforms along the Lantau Airport rail link, on the Singmar Bridge, which is the long suspension rail road bridge, and also at the station going out towards the new theme park out there as well. So again, moving forward in 2002, we were looking at heavy haul applications. We introduced another base plate, which was the Alt-1 design, which we'll see later on. Up to 45-ton axle loads in some areas. In the Newcastle, the Wollongong area where the steelworks are, and also in the Pilbara out the west where they've got high axle loads. These base plates were installed and still there today. We then were lucky enough to get into the Singapore market with our Cologne eggs, which is now the Delco eggs. Moving forward again, we were successful in the late 2000s in North America, mainly in Canada, which today we dominate. We've got work in basically every major city, from Montreal, Ottawa, Toronto, Edmonton, Vancouver. And we're actually going there next week for some other projects we've been involved in. In 2015, with Tyflex, we were lucky enough to be awarded the supply agreement with London Underground to supply the base plates. The first installation was in 2013 in London at St Paul's, Chancery Lane, and St Paul's afterwards. 2017, we started just doing some rubber manufacturing in Melbourne, south of our main head office in Melbourne. We're doing some minor rubber work, platform gap fillers, and rolling stock suspension components. And just recently, in 2023, just last month actually, we signed a contract for the St Paulo Metro Line 6 project, which for us is a breakthrough into the South American market. So that's a brief history of Delco. We have been around for a while. I just want to give you some interesting facts about Australia. There are 24 million people and 150 million sheep. We're home to 21 of the world's 25 most venomous snakes, which is quite scary at times. We have had it in our backyard at home, the brown snakes. They're quite common in some of the cities in Australia. The average person swallows 3 spiders. That's an interesting fact. We have the largest population of feral camels in the world, 1.2 million. And we now export camels back to the Middle East, so there's an opportunity that we found. 90% of Australians live 50 kilometres off the coast, and sharks are immune to all known diseases. So when you go into the water, just be remember that. We manufacture more than 2 million bottles of wine each year, and we export that as well. The first ever police force was made up of most well-behaved convicts, so beware. Prior to 2009, Australia had been under the Sorry, I had to bring it up, and I just think that this is quite appropriate for the time. Just our manufacturing footprint. We initially were manufacturing in Australia. We now have a bigger footprint. Australia, in Sydney, our head office, where all design, quality control and commercial aspects are done. We have the Melbourne factory, which we spoke about before. Our main manufacturing plant is in China. We have joint ventures over there with suppliers, long-term joint ventures. In fact, our main manufacturing facility, TM2 Suzhou, we established that in 2002. And that was established due to the fact that MTRC in Hong Kong had gone back to Chinese ownership, and they wanted us to manufacture our base plates in China instead of Australia. So we established that manufacturing plant back in 2002. So we've been there for over 20 years manufacturing with level 1 suppliers. We do manufacture here in the UK. We hope to expand that in the near future with some of our base plates. Tyflex down at Cornwall do a very good job at the moment, but we have to expand that. We do have a joint venture partnership in India. We won a project in Kashmir a few years back, and we had to manufacture them locally. So we have a joint venture in India. We have exported some products from India to Canada. The quality is exceptionally good, and we may look at expanding that for other regions. And we do have a facility in the USA as well, which has manufactured base plates that have been type approved by New York City Transit. So we are looking at the American market quite seriously. Our two main products, on the left of the screen, we have the Alt-1, which is a compression type base plate, which we'll go through in detail. On the right hand side, we have the Egg, which is the high attenuation product. Both of these products are being tracked long term globally, and have proven to be not only in terms of vibration, noise and vibration attenuation, but also in maintenance. They've been a very low maintenance product in service. Some of the stats on the product. So the Alt-1 has a static stiffness greater than 15, up to about 35 to 40 kilonewtons per millimetre. Has a ratio static to dynamic of about 1.2, which is quite low, which is very important for dynamic performance. We have over 2 million units in service. At the moment, our sales are around 200,000 per year per annum globally, and the first installation of the Alt-1 was in 1992. The Egg, it has a static stiffness range of 6 to 15, so very soft, good for that noise and vibration attenuation. Very low static to dynamic ratio. Over 1 million units in service at the moment globally. Our sales are around 100,000 per annum, and the first installation, as was said, was back in 1984. Those eggs are actually still in track today, and they've actually started to look at a replacement program. Just the fact that they're changing up the whole infrastructure, they want to change the base plates as well. But they're still in service and they're still working. So I'll pass over to Luke, who will go through some of the technical details of the products, and I'll be in the background here, holding some of these.
The hand model.
Hand models.
Yeah, thanks, George. Yeah, so first I'll just go through the Alt-1 and then the Egg, and then just look at some technical points in terms of track resilience in general, and why that's important in this day and age.
So I'll pass these around. These are 3D prints of the product that Luke's talking about. So this is the Alt-1. You can pull it apart and see what it's made of. But it's basically a plastic model.
Thanks, George. Yeah, so the key component that provides the resilience is the natural rubber element, and I'll go into details about that a bit later on. So I guess the initial points, I might just try it this way. So I guess the key point with this Alt-1 system is we can actually configure it to suit whatever the end user preference is. That's in terms of the rail clamping. We can use an E-type clip. If that's the end user preference, we can use SKL12. This base plate is highly adaptable, so we can retrofit this base plate into not every, but most scenarios where you perhaps have no resilience or a lack thereof. You know, for example, we can relocate these anchor tabs. We can move those around to the end to make the base plate narrow, or we can offset these clip housings and make the base plate shorter if we have to. So it's highly adaptable. We have a lot of different variations with different sizes, different rail profiles, yeah, to suit whatever application that you have. So the Alt-1 and any bonded system actually is sort of made up of a few different components. The first being the top plate. So this is an independent top plate that's used to anchor the rail. and that acts separately to the base frame, which is clamping the base plate to the concrete. So the top plate, as I said, we can adapt that to suit whatever rail clamping system you need. It is cast iron, manufactured in automatic, these are cast machines. Typically has a yield strength of about 450 MPa, and an elongation around 15%. So because we have the rubber element doing a lot of the load distribution for the fastener, we don't actually need an ultra high strength steel. So we prefer a steel grade actually that has slightly better elongation. The base frame, it's made of the same material, and again, it's can be highly adaptable to suit whatever anchoring system that you need. And those two components are vulcanized together with rubber. So it forms one single piece unit. You don't have multiple layers of components. It forms a single piece unit. I'll go through how we make these base plates in the next few slides. But I guess the key point to consider with this technology is that this rubber element, the rail clamping, there is no impact on the rubber element when you're clamping the rail. It doesn't come under any preload. And the anchoring, same thing. There's no anchoring that's going through the rubber element providing the resilience. So what that means is that we are able to achieve a very good dynamic stiffness performance because that rubber is not preloaded before you start running any training on it. This top frame, and the best way to describe it, I think George has it good, it works like an engine mount. So we bolt the base to the concrete, the top frame clamps the rail, and then the rubber provides the resilience, similar to an engine mount really. And we have, uniquely with our fastening system, we have this rubber that completely surrounds the top plate. So we're able to absorb lateral and vertical deflections in virtually all directions. So typically, whatever stiffness values that we do have for vertical stiffness, it's quite similar for lateral stiffness as well. Okay, so this is generally how we manufacture a bonded base plate. The top and base frame casting goes through initially a cleaning process. So we'll use a chemical degreasing process. And then the metal parts are also shot blasted. Once that's done, then we apply a chemical locking agent that is basically an adhesive on the components to cast that rubber. We put those components into a heated mould, and then the solid rubber is injected into the mould with a type of heated plunger, if you like. And that liquid rubber flows into the mould. So you can see on the left there, that's a typical time and temperature animation of the rubber sort of flowing through into that mould. From that point, we then cure the rubber with very high pressure and high temperature. So depending on the number of cavities that you have for your for the production, that can be up to 1,000 tonnes of pressure. And that rubber will cure over approximately 20 minutes to half an hour. So it's a very steady, slow curing rate. And by doing that, we have a very, very reliable stiffness performance in mass production. So the Alt1, because of that rubber element, the key feature really is about load distribution, and lateral forces are distributed over a much further distance. And that's really the key for preserving the life of your infrastructure. So we're putting virtually no or little lateral loading transferring through to the rail clips or through to the anchor points. All of that energy is absorbed by the rubber element and that energy dissipated as heat. So the key point with this technology, it's all about preserving the life of the asset. There's less impact on your rails, less impact on your clips, and into your concrete infrastructure as well. So this is a typical load distribution given for a certain axle load train. You have, I guess, the two axles and then the third axle from the next bogie, but we have three plots there. We have a static rail deflection, typical static rail deflection. If you like, an average dynamic deflection with the train passing, and then a maximum. And at the top here, you have the distance. So you can see this rail deflection actually occurs over about 10 metres. So that's, 7 or 8 fastenings is distributing that one wheel load. And that's really the key to the technology. When you have poor load distribution, I've actually pinched this slide from Peter, so thank you. I have to acknowledge when we're using other people's work, but yeah, when you do have poor lateral load distribution, those lateral loads are almost 1-for-1. So there's no load distribution. Those lateral loads are transferred straight into the clip shoulder and then straight into the hold down bolt. And over time, you typically see bolts fatiguing, or in tight curves, you might have your rail clamps or rail clips breaking. Whereas with the Alt-1 technology, all of that energy is absorbed by the rubber. So there's no loads or very little loads going through to your anchor bolts or your clips. I guess this is sort of demonstrated. This is a typical or a legacy resilient fastening system. We're not trying to single any one particular out, but the issue or the difference with the Alt-1 is you see here the anchor that anchors the base plate to the concrete is actually running through that rubber element. So while you may be getting some vertical deflection or some resilience, lateral loads are transferred straight through to this shoulder and then into this anchor bolt. So whilst it may give you some vertical deflection, laterally it's actually quite stiff, which is why typically you either have to have a very large or very strong bolt here if you want it to last any sort of meaningful life. And this is fairly typical in these rail deflection plots here. So again, you can see loads, loads that are different, say vertical loads on the left here between 10 and what might be 60 kilonewton, which is what you might be experiencing with a legacy type resilient system. But that gets even worse when you look at the lateral deflections. So with the Alt-1, typically the vertical and lateral loads deflections are quite similar. Yes. So that's a bit of the theory. I thought we might just show how the Alt-1 works in operation. I hope this comes through okay. It's a little bit laggy, but if you can focus on the foot of the rail, you can see the top plate moving, but there's actually no deflection on the clip, and obviously very rigid or no loads back onto the bolt. This particular example is a 25 kilonewton stiffness fastener that we use in the Toowoomba Ranges in Queensland. That's almost I don't know, 12 to 15 kilometres of a continuous curve going down a steep mountain into the port of Brisbane. So they're running coal trains and freight trains, and the plan eventually is to run double-decker freight trains through this Toowoomba Ranges as well. Previously, you just had a base plate with a pad in that installation, and they were virtually replacing bolts on almost a daily basis. There was a little mum and dad hardware store around the corner up there at Toowoomba, and unfortunately we put them out of business because once they put in the Alt 1, they haven't touched a clip or a bolt now in about 3 or 4 years.
That yellow thing there, it's a new technology base plate we're working on at the moment.
Made of plasticine.
Yeah, it's just to help you visualise the movement of the rail. That's all that was put there. Go for it.
This is a close-up. Maybe this might be a little bit better.
Can you actually see the movement on the screen?
Yeah, I can see.
So you can see it moving vertically and laterally, almost in a similar fashion. And this clip is just not deflecting at all, which with a fairly rigid system you would expect, you know, 0.5 mm of deflection on a tight curve like this. So this was another installation in Toronto, actually. So right down the bottom of Young Street in Toronto, there's a very sharp radius curve that comes down one side of the street, and the railway, for some reason, just turns around and goes straight back up. So right down the bottom of Young Street in Toronto, very sharp radius curve. So the existing fastening system just had a cast iron base plate with a studded rubber rail seat pad. And those clips, again, on that particular curve, they have guys there every night with buckets of clips, just going in there and locking in the clips that have been flying off from the night before. So again, after we put in the Alt 1, we haven't replaced a clip there now in I think 2 years. So they've gone from every night replacing clips to not one for 2 years so far. Okay, so that's sort of roughly the Alt 1, all about load distribution. The next section we'll talk about the egg, which is our high attenuation fastening system. What we're attempting to do, thank you Peter again for the slide. I didn't actually tell you I was stealing some of your slides, but there we go. With the Alt 1, we're actually trying to eliminate this structure-borne noise by eliminating vibration at the track slope. And we're trying to then eliminate that secondary noise, which acts almost like an amplifier when you have the building foundations very close to a tunnel. And I guess more and more in this day and age, it's becoming more and more of a serious issue. So I guess in the past, railway authorities were a little bit reluctant to soften the track too much, especially existing tracks, because that can introduce other issues. But in this day and age now, when we're looking at the track design, this really is becoming a priority. So we've developed a few solutions to reduce the noise and vibration by being able to come in and retrofit a solution like the egg. The manufacturing of the base plate's the same as the Alt 1, with the only main difference being the shape of the rubber profile. So with the internal feature of the egg, we're actually putting the rubber into a combination of shear and compression. So rubber can be quite stiff under compression, but once we put it into shear, it can be quite soft. So we essentially can manipulate this angle of the rubber there to adjust the stiffness and also the rubber compound. And that's really the key difference between the two fasteners. The rubber's operating more in shear than it is in compression, but the manufacturing is essentially the same. You get the same benefits actually with the Alt-1 with the egg in terms of the load distributions. We are deflecting the rail a little bit more, and the effective load on each fastener is typically less. But we have, in some cases, a limit to the axle load. So this fastening system is generally more suited to the Category A, Category B loads. We're not sort of putting these with 20-ton axle loads and above. The vertical and height adjustment, they're the same for the Alt-1 and for the egg. It's quite simple. We don't have to sort of remove a lot of components to do the adjustment, or we don't have to put in asymmetric insulators. We just use a serrated washer feature to give you the lateral adjustment. That can be up to, in some cases on some base plates, up to 15 millimeters. So that can give you almost 30 millimeters of gauge adjustment for both base plates. And sorry, height adjustment is just with shims placed under the base plate. So although it's quite new technology here in London, actually this technology has been around quite a long time. So as George mentioned, Delcor purchased this IP from Cluth back in the 80s, but these concepts of the egg, they are still very much the same. We've optimized the shape and the production ability, if you like, of the base plate, but the concepts are actually more or less the same as they were back in 1981. And you can see the original design actually dates back to the early 70s. So it really is a proven design, although what we're supplying here is slightly different. That concept is the same, and it's been around for decades. So it's not as if it's actually a brand new technology. Now the egg in action. A little bit laggy, but you can still hopefully look at that rubber bulging or the movement there. Again, you can see there's no deflection of the rail clip. We're now actually selling these eggs back to the Germans, who were the original inventors of that technology. I just want to talk a couple of slides actually about stiffness testing and why that's important and why dynamic stiffness actually is important. I'm not sure if this is probably going to show too well, but I wanted to give an example of what that won't work. Yeah, this is an example of high or sort of low frequency dynamic stiffness testing. This test, we compare the static stiffness to the dynamic stiffness at about 10 Hertz with the EN standard. Yeah, it's a little bit laggy. It's actually not too good. So we test to 0 to 35 kilonewtons per millimetre, and we do that at 10 Hertz, and that will give you a dynamic stiffness at that range. So what we have done through some independent laboratories, we have done some, not just dynamic stiffness testing at 10 Hertz, we've actually looked at doing that dynamic stiffness at 250 Hertz and above. And at the same time, we compare that with increasing preload. And what we're trying to do is to compare the fastening systems, how they perform, not just in the laboratory at low frequency, but at the higher frequencies that are normally experienced with a normal train passage. And to do so, you have to look at that high frequency reading with increasing preload to get a true understanding of what that static to dynamic ratio is at those higher frequencies. And as we said with the Alt-1, as you increase the preload, that stiffness ratio at that high frequency actually stays quite similar. So when we quote you a static stiffness of 20, in reality, when the train's running through, it's going to be within a ratio of 1 to 1.5 at that high frequency. Whereas we've tested those sort of double resilient systems, not singling anyone out, of course, but because that rubber element is also experiencing preload from the anchoring, that rubber goes into pre-compression before a train passes, sorry. So when we then test that at high frequency, the ratio actually goes up almost 3.5, 4 times. So while you might be quoted a static stiffness of 20, in reality, the dynamic stiffness at higher frequencies is more like 60 or 70. And that's really a key issue when you're looking at the vibration attenuation, but also for the load distribution. Okay, so this is a theoretical plot. So we have a given rail, 60E1, 20-ton axle load with 2.1 metre axle spacings, and we have a lateral to vertical ratio of 1:1. So what we're trying to do with this plot is basically simulate a tight curve or a train running through a tight curve. On the first y-axis, we have the rail deflection, and then on the x-axis, we have the stiffness. So, of course, as you reduce the stiffness, your vertical and lateral deflection increases. And this is just a theoretical plot based on Zimmermann, so beam on elastic foundation principles. And then on the secondary y-axis, we have the effective wheel load. So as you reduce the stiffness of your fastening system, the effective wheel load on the individual fastener also decreases. But if I go back to the previous slide where we've compared other fastening systems, if you have a 20 kilonewton fastening system in this scenario, you're going to have an effective wheel load on that individual fastener of about 48 kilonewtons. But if with dynamic performance of your fastening system, if that ratio actually, like we tested in the laboratory, is more like 3 times, then your effective wheel load is significantly higher. And more so, obviously, for the lateral loads, because the rail is less stiff bending laterally than it is vertically, if that makes sense. So that's why this dynamic performance is really important. And it's a key point also for that load distribution. Because we don't have that rubber preloaded, that's really the key difference. Hopefully that makes sense.
Yeah, so was QRW?
QRW is the effective wheel load based on Zimmermann.
Okay.
Yeah. So given this axle load train with those spacings and that lateral to vertical ratio, the effective wheel load on the individual fastener, because you still do get some load distribution. So we're calculating using the beam on elastic foundation, calculating the load on that individual fastener. But if your dynamic stiffness performance is not good, then that really goes up. In the next section, George will just go through some of the references now, but this is one of the developments we did here in London, which was to provide a resilient fastening system for the bullhead rail. that was about a 3 or more year process. So this actually had to be past category C. So if you remember, I said with the egg, typically we don't experience or put that into a scenario where you do have high loads. This particular installation, we had to have quite a soft fastening system that was for Moorgate Tunnel, where they had a lot of noise complaints from the residents around. But we had to make it past this category C test, which is a high speed or a heavier axle load requirement because it was a network rail track. So that's really the first application, really, I think, anywhere in the world where you have such a low stiffness fastening system achieving passing that category C fatigue test for the EM. All right, I'm a bit hoarse, so I'll hand back to George now to look at some of the installations. We can talk about more if you have any questions, obviously, at the end with those plots, but hopefully that was self-explanatory.
Thought we had a bit of a freeze up here. Hang on, bear with us. Apologies. It's frozen.
Yep, got the
Dreaded freeze.
white screen of death.
The next section is basically going to go through a range of projects, mainly retrofit projects that we've done, showing some before and after shots, various locations around the world. And then after that, we'll have a questions and answers session.
How are we doing for time? Good. Yes, that one. It's causing an issue. There we go.
So this, as Luke said, this is the bullhead rail egg that we developed for network rail. Took quite a long time to develop. The main issue we had was with the rubber under the category C loads. So we had to redesign the rubber profile, do some FEA analysis, and then eventually we got it to a point where we were very comfortable. One of the benefits that we found with this egg was that with the, what's it called? The key. Under normal operation before the resilience, it used to basically vibrate out, and we found that when we were doing the testing, we saw that this key would stay in place. So there's another benefit there we provided. So this is on the underground. This is going back. The photo on the left is, I think, St. Paul's Station, one of the original. It wasn't the first one. One of the original installations. I was actually on site for the first installation there way back in 2013. You can see the process they used was basically going from the rail closest to the platform across to the other side and then back to the platform. So each night they would only do about 5 or 6 base plates. I think now they're doing about 18 or 20. I think their methodology's changed a bit.
DLR's doing about 20 a night, but I think LU are probably, because it's full breakout of concrete, they're probably doing that because it's 2 metres a night.
Right. The photo on the right is DLR. You can see the legacy base plate in the foreground. The scope that we had was to fit the exact footprint, and in some cases use the existing anchor bolts initially on the Lewisham viaduct. The Dorcor base plates, the black thing, the blue clips in the background. That was developed, it was tested at category A. Again, some development work, because we actually had to shrink the base plate to fit that footprint. It's quite a interesting exercise. This, again, St. Paul's Station, before and after shot. You can see the before on the left and after on the right. I'm pretty sure they're working still today, 10 years, functioning okay. Haven't heard anything. No news is good. No news, good news. This is Norwood Junction Network Rail. This is courtesy of Peter Barber's photos. It's a Alt 1 that was specifically designed for network rail. It's Alt 432 we call it. Heavy axle loads. Category C testing. That wasn't we didn't have to fit a particular footprint there. I think we're just the length.
Well, the reason for designing that footprint was the fact that we were utilising the LU concrete sleeper for stiffness transitions, which we got passed for network rail standards, so that we effectively reduced the amount of components we had to develop for its use.
A Stour Bridge in Kent, again another network rail, same base plate, just a different application.
I think they're the sleepers you're talking about.
Yeah, that's the stiffness transition. You can see the two colours there. So the black ones are the 25 kilonewton, and the green ones in the long distance are the 35. And using the bend radius of the rail, we can actually slowly stiffen it up by using only two stiffnesses.
And stiffness transitions are very important on bridges. People sometimes tend to overlook that fact, but they are very, very important on bridges.
The first stiffness transition we put in on network rail was down at Newhaven, and I looked at the TRV trace after 2019, and there was no noticeable difference between its net on level crossing and stiffness transitions, the same as that. It hasn't shifted, and that's on marine alluvium, fluid marine alluvium, subsoil. So maintainers made up with it.
This is Metro Madrid. More recently, we've been quite busy in Madrid. You can see the legacy base plate behind the Delcor base plate. There you can see the biggest difference between the two is that the Delcor one has that uplift and lateral restraint on the end, and that's where they were having problems with lateral movement. The base plate's been there now for 4 or 5 years at least. And we've also now started supplying the egg base plate into Madrid after doing a very extensive category B testing regime with them in Spain.
They don't tend to take the Aussies' word for it, she'll be right, you know. It's just on a lot of testing.
Yeah, this was the egg being installed or retrofitted in between the existing system in Barcelona some years ago. The main street of Barcelona, where all the fancy shops are, where Mike probably shops most, was a very political noise and vibration. So they looked at our product. We went down there. We looked at what we could do with limited possession times. So we had to basically work in between the existing fastening system. That they tried softer pads and other methods with the existing system, but it just didn't get to where they wanted to. We've put the egg in and it basically solved their problem, so we're pretty happy with the result. This is MTRC Hong Kong. You can recall early on when we talked about our first export back in 1987. The photos on the right, in the middle there, it's the Singmar Bridge. At the time in mid-90s, that was the longest railroad suspension bridge in the world. And the Delcor one was actually a 2-hole system, you can see here, installed directly on the steel girders. They're still in operation today. And that basically gave us a really big foothold into the Hong Kong market. We dominate Hong Kong quite a lot now. The photos on the right, the top one's a retrofit project where we had to again remove the old block system and install a new block in limited positions. And on the bottom there was a greenfield project back in 2005. Name escapes me, but I was on site. So,
West Rail?
no, it's not West Rail. It's got a funny name. I'll embarrass myself trying to announce it. Singapore, SMRT in Singapore. This is a very interesting project. The existing legacy base plate was a double fast clip plate that was installed on the circle line back in the day with a static stiffness of around 25 kilonewtons. And they had a particular location above ground in a particular person's house who happened to be a director on the LTA board, who had some noise and vibration issues in his house. So he made complaints, and the tender brief was to design a resilient system with 7 to 10 kilonewton stiffness that would fit exactly in the same pocket. So utilising the fast clip, so you can see here, a fast clip is utilised to hold the base plate down. Sorry, where's the, yeah. A fast clip is used to hold the base plate down, and a fast clip is used to hold the rail. So the only option that we had was an egg. As you can see here, it's impossible for us to use a fast clip in this area, so we opted for an egg clip design. We worked with Pandrop in this area here to develop a casting to accept the fast clip. We put our tender in, we won the job, so then we had to deliver it. But the two parts of the brief were very, very important. Was that at 40 hertz, you had to achieve a minimum of 6 dBV, so vibration reduction. And at 50 hertz, you had to achieve 9 dBV reduction, minimum. They took before measurements, then they did after measurements. Our prognosis, our calculations showed that we would probably get around 8 to 9 at 40, and possibly 11 to 12 at 50, with a vertical deflection of about 4.48 millimeters to be exact. We actually achieved 8 at 40 and 13 at 50, and the vertical deflection was measured at 4.52, so we were slightly out. But the vertical deflection that we calculate is at the base plate, and the measurement they did was between two base plates, so there's a little bit of rail deflection there. But that was a very important and very interesting project for us. Again, limited time frame for possessions. You can see here these yellow base plates. We had to do a transition from the 25 down to the 7. So we designed a transition. We painted a different colour, so you had a step easy to identify on site. So we went from 25 to 15 to 12 to 9 to 7. This was the previous, in Luke's presentation there, the TTC Toronto. Again, we had to fit the exact footprint that was on site. So you can see the legacy base plate there on the right. It was small. We had to supply a base plate that fits exactly on the footprint in terms of height and bolt centers. And they used the existing bolts, which had been fatigued probably. We took that as a risk. We took it on board, but we had a bit of comfort knowing our base plate has that lateral protection. They've been in track a bit more than what Luke said. I think they first went in January 2019, just before COVID, and they haven't replaced they were breaking clips on a regular basis. In fact, they were going down there, as Luke said, every night to replace the clips on the high rail. We're going there next week to talk to the guys and probably go on site. They have had no reports of any issues to date. And this is TTC Toronto. This shows you some of the conditions our base plates are exposed to. That's actually ice inside a tunnel where they had a flood.
That's solid ice.
And it's actually solid ice. They asked us to give them a 20-year warranty. Anyway, the problem with that is we don't know the acidity of that. It could be salt. They do use salt in the roads over there for the, to de-ice the roads. So it's probably salt and all sorts of things in that frozen water. The base plates are working.
And the train's running that?
Not at that particular point, no.
And there was a leak in the tunnel, so they had to stop everything.
So we'll be there again this
They're
week.
still in track, so they never replaced the base plates. Natural rubber with our formula, we're not so concerned with ultra low temperatures. It becomes more of an issue when it's ultra high. So yeah, it's just a funny photo really for the end of the slides.
And that's about it, guys. So thanks to all the people online and thanks to the audience for attending. We're happy to take questions. There are some prizes for the easiest questions that I can answer. We've got some prizes here to give away. Sorry for the guys online, but yeah, we open the floor for taking any questions. Sure.
What's the limiting or non-limiting for the rail pad? You talked about, that because over the years people have used quite a range of pads between the rail and the base plate.
Yep.
In designing the base plate that you have, do you allow for a particular rail pad or what?
We use HDPE. That's all we use HDPE, and that's all we use. We don't use
any
any
particular thickness, presumably.
Depends. It's on the clip system used. Mainly it's 5mm. We do 3mm in Canada, I believe.
No, 5.
One of the location books, but anyway, 5. We do, yeah. So we can do, but we only use HDPE because the resilient element is what's doing all the work.
We actually don't really even need a rail pad, to be honest, so we can design the clip deflections by adjusting the height of the shoulders. We just are preventing the steel-on-steel contact. So that's
It's
all
just
it is.
that it struck me as something that hadn't come through in the presentation.
Yeah, so it's just to provide a bit of protection, really, just for steel-on-steel. But in America, they don't use a rail pad at all, so the
danger, John, is if you use a soft rail pad in a Delport system, you can get a frequency clash.
Yeah.
You can actually change the frequency to something that's not absorbed by the system and actually create a worse problem you started with. So HDP is extremely stiff.
Effectively an anti-rubber.
Yeah, so it's conformist rather than...
yes, you definitely get a prize for that one. Very well thought out question.
From online.
Yep.
So most of the examples are of bottom-up track construction.
Yes.
Is it possible to use it as top-down as well?
Absolutely. Most of the examples on the photos are retrofits, so they had to be bottom up. But most of our new projects, our greenfield sites, are mainly done top down. So top down is just basically, your temporary rail support system, hanging the base plates off the rail, getting the survey done, and pouring the concrete.
We do have to use, in that scenario, a HDPE pad underneath the base plate, because obviously we can't have concrete going up inside the rub elements, as you can see there. So provided we have a reasonably thick HDPE pad, top-down construction would occur like any other base plate. Yep.
I was going to say, you said high temperatures are a problem. What do you do in likes of Australia, I expect?
Yeah, so
Issues?
in that scenario, we have to make sure we don't have quite a low stiffness rubber. So in the heavy haul systems where we do have the high temperatures, generally they're a higher stiffness anyway. So it's not really an issue because we have, in that scenario, 25 to 30 kilonewtons as opposed to about 6. So the temperature doesn't have quite a bigger impact on the stiffer rubber.
You don't work on it, you're not in any, I think, sort of desert type locations where you've got high swings.
Probably looking at about 50 degrees maximum ambient temperature in the Pilbara, maybe 52, but the rubber's got, is it 70 or no?
It ranges from about, for the very soft base plates, 50 short array, up to 70 or 80 for the stiffer base plates.
So no, we haven't had any issues, we haven't had any reported issues. So I think the range for the rubber is quite high. To get to that higher level, I think there have to be some sort of meltdown somehow. Yeah, they're pretty...
Climate change.
Climate change.
Yeah, I was just going to ask about where you've had noise and vibration issues and you sort of softening the track form down, whether you've had issues like there has been on London Underground where the track form becomes too soft and you end up with sort of quite short wave corrugation and keeping a lot of the noise in the tunnels. Well, that's been an issue in how you go about
Yeah,
managing
so-
that with the egg.
That is really only an issue with the egg where you are running high levels of cant efficiency.
Okay,
So certainly in areas where it's above 110 millimetres cant efficiency. Obviously in the tube you can't really have super elevation. So what happens in that scenario is with our base plates anyway. So when you get short pitch corrugations, that's purely from a frequency clash.
Yeah.
And that frequency clash occurs because if you don't have enough super elevation, especially with the self-steering bogies on a train, the wheel on the outside of the curve has to travel further than the inside. That builds up a torsional resistance in the axle. And when that starts to unwind, it does so at a frequency very close to the natural frequency of the egg. So, yeah, there are ways to mitigate that. So that's really the only case that we have.
Yeah,
It's always in the low leg of the curve,
yeah,
and for that reason. So in order to separate that frequency clash, you can effectively increase the unsprung wheel set mass, which is everything basically below the suspension of the train. It includes the rail. So in that scenario, we've put web dampers in before, basically to add mass to the rail. And then that separates that frequency to a point where it, I won't say eliminates it completely, but it really slows it down. So it can be done. You can have the best of both worlds. I mean, ultimately, as I said before, the priority these days seems to be to solve that issue with the vibration at the buildings, because I guess people on the train with high in-car noise experience that really only once going to work and maybe once coming back, but the person living up there is going to put up with that, every 2 minutes, and you're running trains a lot longer at night now. So I don't think in this day and age the solution is to just ignore it. So we do have some ideas where we can soften the track and solve that issue with the frequency clash. We do have.
I did it a lot using another product, it has to be said.
Yes,
on London Underground, and it effectively reduced the ground wall, but the internal was really
some fastening systems, and again with that dynamic performance. So because our rudder isn't preloaded, we do get that very good vibration attenuation, and in those scenarios, we do have to come up with a solution for that low leg. But we can do it.
You mentioned one of the projects you showed me, a couple of retrofitting between other base plates that were there.
Yeah.
Do you have to take any account of line speed with the new installations? And obviously, the fact that you've got systems, metro systems like that, which are going through a specific time frame, how does that impact in terms of the dynamics?
Yeah, that's more of an installation issue, but it's the same here in London when you're having to either break out the concrete and put new quick setting concrete in.
We're still running the same line speed.
I was going to say, do you have to look at the dynamics in terms of the line speed?
Yeah, design. Yeah,
because obviously you've got this situation.
Sometimes you have to look at the whole retrofit as a whole. So with London Underground, the only way to do it was to cut all the concrete out, put new concrete in, fast set concrete that reached 20 MPa within 1 hour of pouring.
Yeah.
You torque the bolt up to 100 Newton metre torque, which is half of what we recommend. You run the trains the next day at full speed. You come back the next night, do your final torque with a torque wrench, and move on to the next section. In Toronto, they had to run trains, and it was a low speed situation, so they had to make sure that they could do enough in one night. It didn't affect their line running at all.
I'm thinking more of the point, I mean, on the Jubilee, for instance, we had situations there where the track was designed off the tunnel alignment with radiuses and the line speeds were originally designed for that. But when it actually came to the crunch at the end, when it's been installed, the system couldn't cope. Well, the throughput passengers were slowing the trains down as well, certain locations. So then you've got the issue where you're not getting up to full line speed.
Right.
You're impacting the wear on the rail, the rails, and then you really do get some bad wear characteristics.
Yeah, I mean, we do model speeds and input into our model for formulating the stiffness in the rubber profile. So yeah, we do have to take speed into consideration. Generally, if you're reducing the speed, it's better for the fastening system. So it's not really an issue if you're
it's where you're,
reducing
where you're not achieving line speed, or
Yeah.
for reasons you're queuing up and then it's taking
Yeah.
it through and it's just slowing through.
Any other questions?
Got online, yeah. It says, could the Delcor be retrofitted on an existing EF40 PR handrail housings, like the example shown on fast clips, or would the footprint be too small?
Have to see the exact.
Yeah, we'd have to look at the drawings.
The drawings.
But,
But I wouldn't say it's impossible. We can always look at that as a.
in that scenario, I'm not exactly sure where the EF sleeper is, but in that scenario, we had the fast clips clamping a base plate, so we had quite a significant room to fit in the egg. It's just sort of dependent. We do have some minimum. We can't make it, you know.
Yeah, I mean,
unlimited.
if it's like this,
Yeah.
it certainly can't work. You know, if it's, there'd be a minimum line, spacing that we would need to work in the footprint. But it probably sounds a little bit difficult, that one.
I guess the call is get in touch with you then.
Yes.
So whoever's online who needs the answer.
Yeah, by all means. I'll contact Peter Barber, who's local here, same time zone.
So I've got a question and a comment. So look, you mentioned about high cant efficiency, something to be avoided.
Yes.
Do you offer that as guidance to your clients?
Yes, so when we're doing new construction, new projects, we'll go in there and we'll work with the design team to make sure that we combine our vibration modelling with the track design so that we don't have that issue with those corrugations on the low leg. For example, in Madrid, we've got a very soft egg, 6 kilonewton, but because they're removing the ballast, they have plenty of room in the tunnel. We could design the super elevation to limit the cant efficiency. There's EN standards for that as well. Yeah, so there are other methods that we can look at to help where you can't. It's impossible to do it. Not just something like that dampers, but we can look at things like acoustic grinding, just to sort of limit. And there's plenty of standards out there that can help.
And my comment
Yes.
is, and Peter has said this before, but I'll say it this time, something you haven't drawn out in your presentation is the advantage that your system has over other systems when maintainer needs to change the rails. Effectively, they're just dealing with a bog standard rail fastening system.
Correct. Yeah.
And so the staff will probably have all the tools and equipment and the training necessary. They don't have to have fancy compression tools and hold other bits of rail fastenings in place. So it's for the maintainer to change a rail. It's a very understandable process.
It is, yeah.
Unlike other systems.
Like George said, so we generally will work with, say for example, you're using a pan roll clip, that's what you want to use. We'll actually work with pan roll and we'll get that, those sort of deflections, everything confirmed by them. So you can just go on and use what you're using everywhere else. You know, we have no allegiance to one or the other.
Yeah.
So you can buy it yourself, we can supply it to you, or you can source it from wherever you want using all the same stuff. So yeah, thanks.
Hi, following nicely on from Mike's comment, we are maintaining Delcors and bones on the Elizabeth line.
Right.
Looking at re-railing options, one thing we haven't got a solution for is side roller when stressing on the modified one, holding the SKL12 clip.
Right.
Just wondering whether you've had any solutions to that.
Again, that fastening system was a preference from the client. We tried to steer them. Okay, we may perhaps have a preference maybe, but yeah, in that particular scenario, we sort of tried to steer them towards something else.
It's only a preference because it's got less components. I mean,
Well, it was a
a spring
consistency
clip,
with the other.
everyone knows a spring clip's got some advantages. It hasn't got bolts and nuts. Not to say anything wrong with that clip.
Not that I know of, basically.
No, they only chose it for consistency with the rest of the
That's right,
classes.
that's right.
I mean, vertical rollers, if you jack the roll up, put it on a vertical roller, okay, but.
Yeah, the under rollers are fine, it's the side
Side rollers,
rollers.
you just got no space, you got no space in there.
Okay.
No, sorry.
The clerk on
Okay,
Alberto,
yeah.
very much thanks.
Well, on behalf of the PWI, I'd like to express our gratitude to both George and Luke for delivering such an insightful presentation for us today. So we're truly grateful for sharing your expertise with us. You have both kind of demonstrated your expertise and passion about this, which is clearly reflected on how you deliver your presentation. George, you've given us an introduction to the story of Delco, from a company focused on mining sector in Australia to an innovator in the railway industry. You've also given us a couple of interesting facts. So you got, I'm going to highlight that you got almost 3 million in-service base plates. And I'm also going to add that with those figures that you've told us, and accounting that you export half of your wine, it looks like you're drinking 100 bottles of wine a year. So it's interesting.
Sometimes, yes, we're working with certain customers that drive through the drink, yes.
From my experience from when I was in Australia, I do know that you drink a lot of beer too. So,
yeah. As you get older, but you change. I drink a lot of wine, he drinks a lot of beer.
So look, you have a clear delivery style, and your ability to explain complex concepts is really good. So we all could understand, or you can help us understand, get a better understanding of the challenge and the benefits of good track resilience, as well as how kind of the Delco-based plates have made and how they achieve it. It's been very interesting to see all the details, all the examples. They say that an image is worth 1,000 words. You've got plenty of images, plenty of videos in there, so that kind of has helped deliver a dynamic presentation. So I would like to acknowledge your efforts on preparing for this presentation, coming all the way from Australia to present it to us. And so thank you again for your expertise and for being here today. And thank you everyone for being here.
Thank you.
Please get to could you give a warm round of applause to I think some of us are going to go to the Red Lion race. You're welcome to join us. I think this was our last presentation for this year.
This is, yeah, back in September.
We start again in September.
Yes.
No, cheers. What's ticking?
Oh.
Yeah. So you're still